David did a great job setting this up. He talked about the healthcare system, and he referred to the folks that get sick as what happens in the repair shop. But, as he also said, 85% of all the money is spent in the repair shop. I'm going to talk about the repair shop. Because at some point, you're going to get sick. Now, to do so, it's obligatory to show this slide. This is the healthcare curves of cost curves of every country in the world, the healthcare pressures. These are unsustainable, so like Dave, I agree. It can't go on like this everywhere, not just in India, everywhere. By the way, if you're a country, the way you're going to look at your healthcare system is as if you had one of either two problems. Some have both. If you're an emerging nation, what you're going to do is say, well, I have 100 million people or a couple 100 million people who have no healthcare at all. I need to cover those people. I need access. And if you're a developed nation, you're saying, I'm dying with the costs. I need to get costs out. And supposedly this will run you into some beautiful nirvana of a cost-quality world that no one's actually ever reached or seen. By the way, that's if you're a country. If you're a patient, you don't care about this curve. The curve you care about is a little different. You want your care to be efficient, and you want your care to be effective. In fact, what David talked about mostly was in order to get an optimum outcome for you as a patient, we probably have to do something like restructure the whole infrastructure of how to deliver care. This is Dave's graph. I'm going to talk about something different. I'm going to talk about the effectiveness of what we're doing to folks inside the workshop. I'm going to talk about graph B. Got it? To do so, what I'm going to do is talk, first of all, not about the global healthcare systems in the world. They're all over the place. Countries are experimenting. All the different countries have something different. They are diverging like mad, while at the same time, interestingly enough, we as humans are biologically converging. In April of 2011, our species reached a milestone. It's never happened in our species, and that was that more people on the planet died from chronic, non-communicable disease, according to the World Health Organization, than died from infectious disease. It's a wonderful thing. People are living longer. It's fantastic. It's, of course, the success of antibiotics, which may be overused, but that's okay. We won't go there at the moment. However, this biological convergence means that we're going to be living with diseases that are more difficult and more expensive to treat. I'd like to put this into perspective by showing you some graphs, and these graphs I'm going to animate. The graphs are easy to read. The bubble sizes are populations. They are going to run over years. So we're going to start with 1931. The x-axis is income per capita. The y-axis is child mortality, death between the ages of birth and 5 years. Let's see what happens. The colors, of course, correspond to different parts of the world. So ready? I'm going to see if this works. We're going to try to animate this graph up until the present day. Should take a second to run. There we go. So what happens over time, interestingly enough, as you see, is that we started out with child mortality in 1931 across the world. It was all pretty lousy. Everyone was experiencing a huge amount of death of kids. And now what's happened is this is the only graph I'm going to show you where you're going to see this wonderful line. And by the way, the wonderful line tells you a little bit of something about child mortality. It tells you that the greatest influence on child mortality has nothing to do with the repair shop. Reduce child mortality, increase the net incomes of your citizenry so they can eat well, have sanitation, have nice houses, and all of that good stuff, well educated, children will live longer. Let's go to a next one. Next one is body mass index. Going to do the same thing. Here goes. We're going to run it. Oh, we're getting fatter. We're getting fatter. So the entire world is getting fatter, By the way, during the break, if you want to know about Nauru, a small island in the Pacific, I can tell you why that's an outlier. It's a very interesting outlier. But in fact, we are all getting fatter as we get richer. Isn't that delightful? Now let's take a look at one more, blood pressure. This is a fascinating one. Check this one out. Ready? We're going to run it. Ooh, it's converging. Blood pressure is fascinating because what's happening is the wealthy nations are educating their population, don't eat this, eat that, reduce your salt, and by the way, here's some medications to reduce your blood pressure. Where the developing nations, guess what's happening to you? Your blood pressure is going up. Probably before the end of this presentation, I'm going to do this to you even worse. So now, let's try one more just for fun. Cholesterol. Same thing as blood pressure. It's going up in the developing world, going down in the developed world, and starting to converge again. We are becoming biologically similar across the globe. Now, the bad thing about this biologically similar world, and the bad thing about not dying from infectious disease, is you gotta die from something eventually. And the probability is now you're going to die from big chronic diseases. And let me talk about just 3 of them to characterize them a little bit. So the first one I'll talk about is cancer. Cancer is a rare disease. By the way, it's the disease that's very soon going to pass cardiovascular disease. It's the #1 cause of mortality across the globe. Why do I call it a rare disease? It's very simple. If this gentleman has cancer, I don't mean to give you cancer, sir, but I have to. This is necessary, but you might not die. So if you have lung cancer and you have lung cancer, you're going to survive yours. It's okay. The likelihood that the 2 cancers are biologically similar is vanishingly small. There is no cancer. There are cancers, and the multiplicity of these cancers is quite large. There are currently 200 drugs in clinical trials right now that target different genetic mutations of cancers. Therefore, curing cancer will require an individualized treatment that's expensive. And we need to get the cost out of that. We're going to talk about how. And here's, by the way, our understanding of cancer. 100 years ago, if you came into the doctor and you were weak and anemic and pale and just wanted to sleep all the time, you had a disease of the blood. 80 years ago, we recognized this leukemia and lymphoma. Today, there are 100 different types of these diseases, each with an individualized treatment. This fine splitting of the disease of cancer could drive costs up, or it could drive costs down, depending upon how we act. How about cardiovascular disease? Cardiovascular disease is an easy one, right? Because we know what causes it. Yes, there's genetic predisposition, but it's likely our behavior. By the way, I don't need a mobile device to tell me I shouldn't do these things. I got a wife. And therefore, we know how this gets. Yeah, you too. If the cancer doesn't get you, it's going to be, yeah, well, it's... I'm going to pick on you through the entire presentation. Is that okay? Okay. I hope you don't mind. You seem like a good sport. But I think I can outrun you. So good. We're good. Cardiovascular disease actually has made terrific strides in reducing mortality. And in fact, I would contend that here Dave's solutions might be more appropriate than new technology solutions, because we don't have uniform applications of the current standards of care and current technologies. Use those and we have a huge opportunity to reduce mortality and morbidity from cardiovascular disease. But if you survive both of those and you live to the age of 80, guess what? You have a 1 in 2 chance of suffering from dementia, which over time erases your memories and erases who you are. We know something about this disease. We know that there are 2 proteins typically involved, beta amyloid and tau. We don't know really their role, whether or not, as if in a crime scene, they're witnesses, they're bystanders, or they're the criminals. We see that some people die upon autopsy. They have horrible dementia, no beta amyloid. Some people, brains full of beta amyloid, they are perfectly fine. We don't understand the disease perfectly. I believe progress against these chronic, expensive illnesses that are going to be the drivers of your healthcare system costs require 4 things. New technology that dramatically increases diagnostic specificity, large number of patients for clinical trials to figure out if they work or not, large numbers of scientists to curate that data, and solving difficult data and IT challenges. I'm going to go into detail about each of these briefly. First of all, diagnostic specificity. The trends in diagnosis over the past 30 years have been very uniform and unidirectional. Diagnose things earlier, smaller, faster, before you have any symptoms whatsoever, and that's a good thing until it's not. This is a case of where it's not. South Korea has had, seemingly, an epidemic in thyroid cancer. Look at that. We don't know what it is. Is it Fukushima? Is it what's causing this huge? But if you look at the lower curve, that's mortality from thyroid cancer. Flat, not budging. There's only 2 explanations for this curve. One, the South Koreans are magnificent at diagnosing thyroid cancer and curing it at exactly the same rate every year, leaving mortality alone. That's one explanation. The other explanation is that around the year 2000, they introduced high-resolution ultrasound screening for thyroid in the annual physical exam. Now, sir, when your physician comes to you, I told you, you're going to get this the whole time. When your physician comes to you and says, sir, you have a small spot on your thyroid. It could be nothing, but it could be a lethal disease. Thyroidectomies are no big deal these days. We'll just remove your thyroid. You'll have to take this medication for the rest of your life, but you will have no worries anymore. Guess what? We're removing thyroids. And they're unnecessary. We need a diagnosis that will tell us which one's necessary and which one's not. We will save huge amounts of money, and this is not the only disease where that's the case. Here's another interesting example, fascinating example. If you remember back to the early 1990s, there was this weird disease coming up called AIDS. It was going to be an epidemiological catastrophe, a problem that could just stop mankind. And what happened? It is now a chronically manageable illness. What was the one single breakthrough? Simple. A diagnostic test that say that you have AIDS, along with your cancer, and you do not, with perfect 100% accuracy. Now, imagine the following thought experiment. We want to develop a drug to treat AIDS, or a cocktail of drugs. And imagine the diagnostic has the same sensitivity and specificity as most of them. In other words, they overdiagnose by a factor of 3. So now you have 100 people, 33 have been identified as having AIDS. No, all 100 have identified having AIDS, but only 33 actually do. Now you put a drug into a clinical trial. It cures 50% of the people. You put a second drug in a clinical trial. It cures 33 people. Oh, it sounds like that 50% drug is better. But if you don't have the specific diagnosis, you're done. In addition, it leads to controversy. We have standards of care that are being debated and overused. If you look up, read your New York Times from this morning. This morning's New York Times front page says long-term clinical trial, breast cancer, in situ ductal carcinoma. They followed large groups of women who have had mastectomies, lumpectomies, and radiation therapy, and another large group of women who had nothing. Survival rates were identical. Here are women, so forget the cost for a minute, women who are succumbing to horrible, invasive, nasty medical care with huge expense. Survival is unchanged in the 2 groups. Of course, this has ignited a huge controversy, but it's a data problem. It may actually be a problem that there is a certain type of cancer which will kill you, and another not, and we're just removing all of them. These are the top 10 drugs in the United States by revenue. The blue is the number of patients that they actually help. The white is the number of patients who get it anyway. Now, if I'm a pharmaceutical industry, I love this graph. But if you're a patient, you hate it. And if you're a healthcare system, you hate it. By the way, just show of hands, who in the audience has themselves or have a family member have the following conversation with a physician? Conversation goes something like this. With your symptoms and these test results, I think you have disease X. Take this drug. Give me a call in 2 weeks, we'll see how you're doing. Right? Everyone's had that conversation. You have just been made an experiment. And that's a very uncomfortable thing. It's wasteful, it's bad. You don't want it. So the task is ultimately, out of a large audience of people who have a disease, to find out through diagnostic methods who actually does have the disease we're trying to treat, and then find out how to group those together and do population-based studies on small cohorts, subpopulations. Step one. There are technologies available. New technologies that 10 years ago weren't there. The omics revolution. Human genome has been encoded, took us 2.7 billion, 10 years for 3 billion base pairs, a buck a base pair, what a deal. And if you do genetic testing, it generates a huge amount of data. New detection technologies for new imaging, more data. Wearable devices, I'm going to longitudinally track everything I say and do, my entire physiology, more data. I'm going to have targeted therapies, but I need to monitor it and titrate how it's used. Data. And now I'm going to aggregate all of that stuff together. Huge data. By the way, I think there's a country in the world that knows something about IT. I don't remember where it is. Quick little aside. If you do genetic testing for disease in order to find out the genetic profile, it sounds like sort of a high-tech automated thing. So Dave hinted at this. I can only support him. And here's a little, this next slide is a screenshot. You can't read it. It's an actual screenshot from a database of a genetic testing company. On the top, you see different patients, what cancers they are said to have, and over on the side, what mutations those cancers have. This first patient has a lung cancer, and actually, if you can read the text down below, and I don't expect you to be able to, they have a mutation for which there is no drug available for that lung cancer patient. There is, however, a colon cancer drug for that mutation. So interestingly enough, is without this genetic testing, that patient was doomed. With the genetic testing, they get a clinical trial for a colon cancer drug that can help them. But here's the little secret. I'm going to blow up one part of this graph. Let me blow it up right here. And when you blow it up, the top patient actually had 859 mutations. The 859 mutations were automatically curated by the IT 842 times. 17 of the mutations required a human to look at each of them, a skilled PhD biologist, and actually make a decision and input that back into the algorithm. This is a human-intensive, a highly educated, human-intensive problem. I think there are countries in this world that have a lot of well-educated people. I don't know where that is. Mobile healthcare. I totally agree with what David said. Totally agree that the majority of mobile healthcare is crap. And the reason it's crap is that the great majority of mobile healthcare addresses a target audience at below. Now, what do I mean by socially complex versus socially simple? The majority of you folks are socially simple people, I assume. By socially simple, I mean you have jobs, you have families, you have homes, you have a support system, you have routines. you're well educated. And you wear a little device on your wrist that tells you how much you want and what your blood pressure is doing and everything. And once again, I don't need that, I got my wife. But that's the target for most of these devices. And by the way, most of them have a precision of almost nothing. Now, the costs are there. So the difficulty is we have a technology gap. My belief is actually the biggest immediate opportunity is move into that quadrant. Folks that are still socially simple, but just come down with cancer. And now that has to be addressed by him. And by the way, there are companies that do this. For example, I'll give you two. AliveCor, little device, ECG device, claps onto a cell phone or a smartphone, measures ECG. Instead of just having ECG for all diseases, what Ewan Thompson, the CEO of this company, a good friend of mine, did, is he said, I'm focusing on a single disease, atrial fibrillation. I'm going to give away 2,000 of these devices to folks with tachycardia. And the 2,000 folks with tachycardia are going to give me the ECGs. That device can now diagnose tachycardia better than Cleveland Clinic's physicians in a side-by-side test. Amazing. Atlas 5D, one of the companies in our portfolio, has a little device which has such high-fidelity motion measurements, it's now being used in clinical trials to be a companion diagnostic for motion disorders. But it has to be very precise, very high fidelity. But these are cool things. By the way, I engaged in my own experiment some time ago because if you integrate data, some cool things would happen. What I did is I said to my old friends at Siemens, image with everything you make my heart. First of all, to demonstrate I have one. But secondly, we're going to put the data together. And when they did so, the result was a fascinating result. This is an image that does not exist other than in silico. It actually shows the blood in my heart and how it is traversing the chambers of my heart. Nothing can image this except with the integrated of data, you can simulate it. So the potential is enormous because instead of having something big and fancy, you do it. Now, what are the requirements for success? And I broke this into sort of two parts, right? So there's, what David talked about mostly was India's medical problems, our healthcare problems for India. I actually had thought about it a different way. What can India industry do for the world? And frankly, I said these are the four keys for success, and I think you got at least 3 of them. And if you work a little bit, you can get the 4th. There's no reason this country can't dominate a good chunk of this industry. And by the way, there are already companies that are incubating who are trying to do this. This is a company which has 1 foot in the United States, 1 foot in India, and basically attempts to do data integration for very complex disease. Ladies and gentlemen, this was a fast ride through a technology landscape. I hope it was at least amusing, if not slightly correct. And I thank you very much for your attention, but I will say humans are complex.